How can a VFD stop the motor connected to it? What are the differences between the various braking methods? If you want to find the answers to these questions, stay with us until the end of this video. Let's assume a VFD is connected to a 3-phase motor. In the image, you can see a simple connection between the motor and the VFD. In this video, we're going to show you how a VFD can stop a 3-phase induction motor. The braking methods for induction motors can be divided into 5 categories. 1. Coast to stop. 2. Controlled stop. 3. DC injection brake. 4. DC dynamic brake. 5. Regenerative brake. Each of these methods has its own advantages and disadvantages, which we'll discuss in this video. The choice of braking method depends on 4 factors. 1. Mechanical load. 2. Stopping time. 3. Energy requirements. 4. Cost. Before we dive into the braking methods, let's first look at the mechanical torque equation between the motor and the load. In the image, you can see the motor output torque, load torque, system inertia, and angular acceleration. During motor startup, the motor torque is greater than the load torque, resulting in a positive angular acceleration. When the motor and load reach a steady state, the motor torque equals the load torque, and angular acceleration becomes 0. When we need to stop the motor, the total torque must be negative to create negative angular acceleration. The higher the inertia, the smaller the angular acceleration, meaning the motor will take longer to stop. Now, look at the graph displayed on the screen. This curve represents the motor's torque and speed. In this graph, you can see the motoring region and the generating region. The boundary between these two regions is the synchronous speed. If the rotor speed exceeds the synchronous speed, the induction machine behaves like a generator. If the rotor speed is less than the synchronous speed, the machine operates as a motor. Now let's examine each braking method. First method. Coast to stop. In this method, when the VFD receives the stop command, it cuts off the voltage applied to the stator, and the motor and its load continue to spin freely until they eventually stop. The stopping time depends on the inertia of the motor and load. This method is suitable for applications where stopping time is not critical. For example, if the inertia of the motor and load is high, it may take several minutes for the motor to stop. When the stator voltage becomes 0, the motor's output torque also becomes 0. The stored energy in the mechanical system is dissipated as heat and vibrations in the bearings. Second method. Controlled stop. This method is suitable for light loads such as centrifugal pumps, fans, blowers, small packaging machines, and more. The stopping time can be set in the VFD's parameters, but it should be appropriate for the combined inertia of the motor and load. When the VFD receives the stop command, it gradually reduces the stator voltage and frequency over a specified time and slope to stop the motor. If the inertia is high and the stopping time is set too short, the VFD reduces the frequency, but the rotor speed doesn't decrease accordingly. In this case, the slip becomes negative, causing the motor to enter the generating mode, which can result in overcurrent in the VFD. As shown in the equation, the motor torque after the stop command is not 0 but is less than the load torque. This creates negative torque, leading to negative angular acceleration and causing the motor to stop smoothly without mechanical stress. However, the energy stored in the system is still dissipated as heat in the mechanical components and bearings. Third method. DC injection brake. This braking method is suitable for loads with low or medium inertia, such as centrifugal fans, conveyors, and similar systems. In this method, after the stop command, the VFD applies a controlled DC voltage to the stator. The VFD must control the stator current. It's important to note that an induction motor always generates torque to bring the rotor close to synchronous speed. The principle of DC injection braking relies on this behavior. For example, if the motor is running at normal operating speed and the synchronous speed is suddenly set to 0, the motor generates braking torque to bring the rotor to a stop. In this method, strong currents are induced in the rotor. As the rotor speed decreases, the magnitude and frequency of these currents also decrease. Looking at the torque equation, we see that unlike the previous methods, the motor generates negative torque. This negative torque creates significant negative angular acceleration, allowing the motor to stop quickly. The VFD must control the stator current throughout the process. One advantage of this method is the rapid stopping due to the generated negative torque. However, this also causes heat buildup in the rotor, as most of the system's kinetic energy is converted to heat. Fourth method: DC dynamic brake. This method requires the use of a braking resistor. Additionally, some VFDs do not support this type of braking. In some cases, a braking control unit must be installed along with the braking resistor. The resistor dissipates the energy extracted from the mechanical load by the induction motor during stopping. This method is suitable for most types of loads and significantly reduces stopping time, including loads such as large piston compressors, large conveyors, high-rise elevators, etc. However, in elevators, braking resistance is also used for other purposes. It's particularly effective for loads with high inertia, allowing them to stop in a short time. The principle is that after the stop command, the motor enters generating mode. The VFD's IGBTs switch in such a way that the energy from the motor is transferred to the braking resistor. In this mode, the inverter section of the VFD operates like a 3-phase AC to DC converter. During braking, the synchronous speed is always lower than the rotor speed to keep the motor in generating mode. One question you might have is whether the DC link capacitor is essential for this braking method. Share your thoughts in the comments. In this method, both the motor torque and load torque are negative, resulting in significant negative angular acceleration. Fifth method: regenerative braking. This method is similar to DC dynamic braking, but instead of using a braking resistor, the energy recovered from the load is stored in a battery. This improves efficiency and is often used in electric vehicles. Since the energy available in the battery of an electric vehicle is limited, regenerative braking is essential to enhance overall efficiency. In this video, we covered the braking methods for induction motors. Here's a quick summary table for your reference. If you found this video helpful, please support us with a like and subscribe to our channel. Don't forget to share your comments and questions. We'd love to hear from you.